All right, so welcome back. Let's get started, shall we? I took a quick look at the midterms. They look fairly good, I think. You've fairly figured it out. I only took a quick peek. It will take us a while to actually grade everything, because now there is like a lot. So we are entering the more exciting part of the course when we will do determinants, eigenvalues, eigenvectors, culminating with SVD, which is sort of cool. Some people are asking about the final exam. I posted on Piazza. It's going to be December 15, 3 to 5, assuming PM. Doesn't really say. You would assume that. Some people were also asking, on a more general level, what is the relationship of EAS205 and these similar math classes like 240 or 312 and 313. So we discussed this a little bit. I discussed it with the guy who was teaching it before me, because I only started teaching it last year, this course, so I don't have all this historical perspective. But it turns out that the Math 240 is like the very basic stuff of this. Basically, it was designed as a preparation for physics and vector calculus, to give you an idea what are like 2x2, 3x3 matrices. So then you can go on to vector calculus and do things like div, grad, curl, so you know your ways in vector calculus. So that's not quite the same what we are doing here. So this course was essentially done so you have the background necessary for like graphics, vision, robotics, machine learning, all these courses offered at computer science. Like I'm teaching phys-based simulation in the spring, and I always struggled with people not knowing enough linear algebra. So that's my personal motivation for teaching this. There's also Math 312 and 313, and those are good. In 312, you will get probably like a deeper mathematical background to linear algebra, but you won't really get the numerical computational aspects, let alone some MATLAB program. It's going to be like purely the math part of stuff, math side of things. And in Math 313, you would get some more of the numerics and the computational aspects, which I guess is okay. If you want to go like applied mathematics and do like computational science or something more serious like that, scientific computing, then that's probably the good way to go. But if you just want the necessary background to be able to continue studying graphics, robotics, vision, machine learning, and you want to be solid in linear algebra for these type of classes, then I think EAS205 is the way to go. So I guess that hopefully addresses some of the questions some of you had. Okay, any other questions before we dive into determinants? All right, so let's do that. So let me start actually not on the slides, but by explaining sort of on a high level what a determinant is. So determinant is a function from a square real matrix. We could also define it for complex matrices, but let's stay in the simple case first. So it's a function which takes a square matrix, n by n matrix, and produces a number. So you can think about it as a way to characterize, to sum up the matrix in a single number, in a single scalar, real number, of course, in this case. So I guess I think we talked a little bit about determinants already, right? I think I gave you the formulas for the 2x2 case, and maybe even the 3x3. Those are very easy. Actually, even easier is in the 1D case, right? So if n equals 1, what do you think would be a determinant? So we are talking about 1x1 matrices. It's sort of funny because the matrix is just like a single number, right? So what would you think should be the determinant of 1x1 matrix, just by like common thinking?
A.
Yeah, exactly, the number itself, and that's absolutely right, yeah? So the determinant of this funny, it's like philosophical if you should even be calling this a matrix, right? But indeed, the determinant of this will be just the number itself. And it gets more interesting if we go to higher dimensions. So in n equal 2, I think I told you what a determinant is, right? So we are talking about a 2x2 matrix, so I can call its elements A, B, C, and D. And I think I told you before that the determinant is AD minus BC for a 2x2 matrix, okay? So here it's more interesting. What's happening is we are taking a 2D matrix and we're extracting a single number of it. And this number is quite important, as I would like to argue later on in the class, okay? It even has like a geometric interpretation, but I don't want to get ahead of myself. It's probably you could say it's the number that tells you most information about the matrix, in some sense. Okay, so how do you think that generalizes for a 3 by 3 matrix? Do you know this? How to do a determinant of a 3 by 3 matrix? If I have matrix A, B, C, D, E, F, G, H, I. These are just some scalars, right? A, B, C, D, F, G, H, I. Those are scalars. Don't confuse this with the complex unit. That's not meant to be complex unit. It's just a scalar. So what is the determinant of a 3 by 3 matrix? Do you remember it? You must have seen it, maybe. Okay, so you already know some determinant rules, so you're sort of getting ahead of ourselves. Well, for 3 by 3 matrix, I can just write it like this. I like go like this: A, E, I plus B, F, G. And I will later explain how exactly this is derived, where did this come from. But let's first look at it and try to reason about it. Minus A, H, F, and the last one is D, B, I. Okay. So the first thing I would like you to, I will show you where did this come from, but for now you can just take it as a fact that this is how you compute the determinant of a 3 by 3 matrix, okay? And one thing I would like to you to notice is here I have one term, right? Just A. Here I have two terms. I have AD and I have BC, and I take their trivial linear combination, okay? Here I have 6 terms, right? So can you start noticing a pattern there? If I like write down like a sequence of numbers 1, 2, 6, what do you think would be the next number in the just by? Yeah, that's a great point. And what do you think would be the one after that? Once you go 24, we'll get the next one too. 120, that's correct. So you correctly guessed the pattern there. So indeed it is n factorial, the number of terms. And this is what the big formula, which we will eventually get to, this is what the big formula will do. And this is also, I guess, the reason why I don't want to start by just giving you the formula for the determinant for the n by n case. That's what we, of course, want to consider, the n by n case, where n can be a large number. But already from this, you can see, and again, we didn't quite argue why this is the case, it's just by sort of like looking at it and thinking about it. But if this is true, then like for n equal 10, the formula would have like an insane number of terms, right? Like 3 million or something like this, whatever is factorial of 10, right? So this formula is probably not going to be the easiest way to think about determinants, right? Because it has a lot of terms. Sometimes it's useful, but it turns out that probably more useful is to think about determinants in terms of its properties, okay? And there's going to be a more efficient algorithm how to compute determinants. So in the following, what I would like to do is to, instead of just giving you the formula how to compute it, defining the determinant by the formula. In 2D and 3D, it's sort of easy to define a determinant by the formula. I have a formula for general n, and I will write it down later. It's called the big formula, or that's how Gilbert Strang calls it. But it turns out it's actually easier to reason about determinant instead in terms of its properties. As a function, which I don't write it down explicitly, I don't give you the formula, but I tell you that the function exists and it has certain properties. So that's what I'm gonna do here, okay? Actually, align it a little bit better. So this is what I said before. Determinant, keep this in mind. It's just a function, okay? Takes a square matrix and gives me a real scalar value. We're talking just about real matrices now. Oh, there is a notation for determinants. So this can be sometimes confusing. This is like a quick notation for determinants. So if I could also write it like this, like A, B, C, D, and these bars mean take the determinant of it. So I could write things like this. This is just like a shorthand for the notation. I don't like it super much because then it gets easily confused with like this means the matrix, right? Just because they are like square brackets. But sometimes you can see this and just apply to a matrix. The other reason I don't like this notation very much is it can get confused with absolute value, right? But a determinant is nothing like absolute value because it can easily be negative, right? Of course. But anyway, that's the standard notation, so we have to live with it. regardless of whatever my opinion of that is. And the important thing here, the notation might be negotiable or debatable, but the defining properties, they are important. So there are three. So this is what I said before. I want to define determinant as a function which satisfies certain properties, and here are the properties. So first is fairly obvious that for identity matrix we want the determinant to be 1. Okay, that's now we are defining determinant. Okay, so these properties are defining properties, sort of like axioms, sort of like we had before when we talked about vector spaces. I gave you this laundry list of properties it needs to satisfy to be called vector space, right? So it's the same idea. I give you like a list of 3 properties here which the function needs to satisfy to be called a determinant. Okay, and turns out that actually the function is then defined uniquely and it exists, so it's like a perfect specification of the function. So the number 1 is that determinant of identity is 1. Number 2, very important, if you exchange 2 rows of the matrix, you change the sign of the determinant. Okay. Later it will turn out that it doesn't matter if I wrote their columns and formulate everything in columns instead, I will get the same thing. But for now you can even forget about it and just think in terms of rows, and later we will prove that the same thing is true for columns as well. And the third property says that the determinant is linear with respect to every row or column. So with this linearity you need to be very careful, because the worst possible mistake you could do would be to assume that determinant is linear function. So here I told you the determinant is a function, right? But it's absolutely not linear, right? As I guess only in the 1-by-1 case it's linear because it's just identity, that's a dumb function. But already in 2-by-2, the determinant is definitely not linear. How can we see that determinant is not a linear function?
When you multiply the entire matrix by a particular number,
Mm-hmm.
it's not that product as well, determinant, because it's
Right. But yeah, but for this we will sort of need what I'm going to derive later. You are absolutely right, but I can give you a more basic argument, I guess. So just take a look what is determinant of identity in 2D, right? Oh, you know what? Let's practice this funny notation, this notation, 1, 0, 0, 1. I guess I will be using it because it's just so convenient, right? So determinant of 2-by-2 identity, of course, is 1, right? Now, if I take identity and add it to identity, I plus I, it's funny in this notation, but okay. So that's matrix which looks like this, right? So what's the determinant of that, of matrix 2, 0, 0, 2? 4, right? Well, 4 does not seem to be equal to 1 plus 1, right? Which would be determinant of identity plus determinant of identity, right? And for a function to be linear, it would have to be true that you can either apply the function first and then sum, or first sum and then apply the function, right? We talked about linearity at length before. So definitely the determinant is not going to be linear. So what did I mean by the linearity here? Well, what do I mean by the linearity here is linear with respect to every row or column of the matrix. Okay, so let's see. Okay, maybe I can write it down a little bit better than here. Well, this is probably okay, right? So this is okay. So what I mean here is if I have a matrix and these VT and WT, that means those are just 2 row vectors, okay? So that means that I can split this determinant into determinants of 2 matrices, okay? One has the one part, V transpose, and the other one has WT, okay? And they are multiplied by alpha and beta. So it's linear, but only with respect to a fixed row, okay? And from this you can also later prove, you will prove that the same is true for columns as well. So that's what's meant by linearity. So for example, for example, the linearity means that if I have this, if I have TA, TB, CD, 2 by 2 case, then the determinant is equal to just T times this. Okay, that's what the property 3 directly implies, right? Because this first row is just multiplied by T, and this says that I can take the T out. Okay. Similarly, if I had a matrix which was like A plus some A prime, and here B plus B prime, and C and D, and take the determinant of that, then by this property tells me that I can split it into two determinants. One will be A, B, C, D, and the other one will be A prime, B prime, C, D. Okay? So that's what this means. By the way, you can, I guess that's what you were alluding to. So we can directly derive it from the first property, right? So if we take, for example, if we take any matrix and we multiply it by T, what do we get in case we already know the determinant of A? I guess that's the question if you really got the third property. Okay, let's do it first in 2D. Okay, so let's say that for a second that A is a 2 by 2 matrix. So, and T is a real scalar. And I'm curious, what is the determinant of TA if I already know the determinant of A?
T squared.
Correct. That's T squared determinant of A. Everybody sees how did I get it? Just applying this property twice, right? It's linear with respect to every row. So I first applied on first row, took the T out, then on the second row, took the T out, I got T squared. Okay? And in general, if A was not 2 by 2, but it was n by n, what do I need to change here? T to n, yeah, of course. It's as simple as that. Yeah, later I will show you that the determinant has a beautiful geometric interpretation that is connected to volume, and this sort of makes sense, that if you multiply something by T, then you will like multiply in all dimensions. I'll explain it better later. Okay. So remember the three defining properties of a determinant. Okay, so determinant identity is 1. If I swap rows, I flip the sign of the determinant, and the determinant is linear with respect to every row or column. But we can prove that. So then now what we are gonna do is we will question?
In the two examples on the left, why?
These guys?
Yeah, like why isn't the T distributed to all of them, and also why, like on the next row, do you add C and D to C and D again?
So do you mean the first one or the second one?
Well, both of them. Wait, is that an addition? Isn't that like wouldn't C and D plus C and D get 2C and 2D or something?
Well, I'm talking. Oh, okay. Maybe I confused it. This means determinants.
Oh.
Yeah, maybe I confused you. That's what this is. This confusing notation. It's just this means determinant of this matrix, and this means determinant of this matrix. So like if I'm a compiler and I'm to interpret the types, this is a scalar. This is a scalar. This is a scalar. So this is just a scalar plus scalar. Okay. Yeah. So sorry about the. That's why I was pointing out. Don't be confused by these vertical bars. They mean determinant of that. Okay. Determinant takes a matrix and returns a scalar value. So I guess you know what, you could prove this directly, right? If you wanted, you could prove this like this. So for 2 by 2 matrix, I can write the determinant directly, right? So this matrix, this equality is equal to this: A plus A prime D minus B plus B prime C, right? That's on the left-hand side, and on the right-hand side, I have AD minus BC plus A prime D minus B prime C, right? Yeah. That's what this means. You can clearly see this is true, right? I need to apply distributivity. Okay, good that you asked, because I will be using this notation just because it's convenient, more convenient than writing these debts everywhere, right? So don't make that confuse you. Yeah, it's too bad it's like similar to matrices, but that's what it is. All right. Any other questions? That's a good. Every question is good. There is no such thing as a bad question. I was always worried when I was a student myself that I would be asking something that will like show that I didn't get it. That's actually stupid. So thanks for asking. Okay, so what are we going to do now? We will take these three defining properties and we will see what other properties follow from this, right? Like we always do in mathematics. So sort of those are our like axioms now, if you will, and we will see what follows from it. It turns out that lots of nice things follow from it. I guess in particular, maybe I could do a little bit of motivation. In particular, we will find out how determinant connects to the notion of singular matrix. I think I mentioned it before, that the determinant tells us whether the matrix is singular or not, which is something we talked about before, so you'll be immediately able to connect it to something you already know. Okay, so let's prove some basic properties of determinants from the three defining properties. Okay, so please try to remember them. So the first fundamental thing is that if two rows, this is sort of funny, maybe I should have written everything for rows and then later said you can also sort of transpose it to columns. I guess it would be better if I just put now all the columns in brackets. It doesn't really matter. Let's just talk about rows for now. If two rows are equal, then the determinant is 0. That's my claim. But now it's not the definition, now I have to prove it, okay? Because I claim, this is like a lemma or something. And now I claim this follows from the definition, okay? So let's see, how does it follow? Well, the property 2 says that if I flip two rows, then it flips the sign, right? But if the rows are the same, then it doesn't change anything, right? Flipping the rows. I get the same matrix back, so it must have the same determinant. So that means that the determinant of A must be the same as minus determinant of A, right? Because flipping rows was supposed to flip sign, right? But the only number, and determinant of A is a real number, the only number that's equal to its minus is 0, okay? So there's no other way to conclude, no other possible conclusion that the determinant of A is 0. If A is a matrix which has two identical rows. Okay, for example, like if I have a matrix like 1, 2, 1, 2, can immediately tell me the determinant is 0. Of course, this is more useful for larger matrices, not for 2 by 2, where you can sort of immediately see everything. Okay, got it. Here is the second property. I guess if we were like in a math, I would like write like a lemma and then like a proof, and then I would make like a little square. It would be like the mathy type of structure. The other statement I want to make is that adding a multiple of one row to another does not change the determinant, interestingly. So, okay, maybe I can write this a little bit better. I can write it like this. So here I have, okay, again, don't let that confuse you. This is a determinant of a matrix, okay? And the matrix, I have a matrix A. Okay, so now this is a matrix. And it has some rows, right? Some row here. And here is a row I'm interested in that's called AI transpose. So that's one of the rows. And here I have another row which I call AJ transpose, and maybe a bunch of other rows, okay? And what I'm gonna do, so what I mean here is that I will create another matrix which will be exactly the same as A, except that this jth, okay, this was row number I, this is row number J. The row number J will now be a linear combination of these two. So actually I will just add, I'll take AJT and I will add a multiple of AI transpose to it, okay? And you know what, let me just write it with the standards. And I claim that the determinant of this matrix is the same as the determinant of A. I guess I could write it like this with a different notation, okay? So why that is true? Well, let's see. So we first apply the property number 3, right? That the determinant is linear with respect to any row. So we apply it with respect to this row. And I will get the matrix A here. And here I get plus alpha times a matrix. Okay, maybe I can write it out to make this clearer. So I'm computing this determinant, applying the property number 3. And I will get that this is a matrix which is just AIT, AJT. So this is exactly A, plus alpha times a matrix, which looks like this. It has AIT here, and it has AIT here. Okay. Oh, these are square matrices, sorry for my sloppy writing. Oh, when we are talking about determinant, we are always talking about square matrices, okay? So what's the determinant of this matrix? Well, that's what we have just shown, right? Here, I just said that if the two rows of A are equal, then the determinant is 0. So the determinant of this matrix is 0, okay? So that means that the determinant of this matrix is indeed the same as the determinant of the original matrix. In short, in summary, if I take a multiple of a row and I add it to another row, then the determinant does not change, okay? So this is second important property derived from the defining property. So let's keep that in mind. Did you get it? Or shall I explain it better? It's basically, it's all written here, right? So just so you apply linearity with respect to this row, you will get the same matrix here. So it's a determinant plus alpha, the determinant of a matrix where there are two repeated rows, which is 0. So the determinant doesn't change, okay? Here is another one. Okay, so yeah, this one is easy. Here I claim that if I have a matrix where each row, let's forget about the columns for now, where each row is all zeros, then the determinant of that matrix is 0. And the way you can prove this is again from the linearity, from the third, from this property, because it's like a little trick. Because the 0 row you can just write as scalar multiple where the scalar is 0 times some arbitrary vector. Doesn't even matter. I can just pick vector of all ones, of all zeros, doesn't really matter. And by linearity, you know that this must be 0 times the determinant of that matrix, right? Well, at this point, it doesn't really matter what the determinant of this matrix is because it's multiplied by 0, so it certainly must be 0. It's like a funny type of argument, but nobody can argue with that. Okay. And what I'm trying to slowly build up to is to a way how we can compute determinant of an arbitrary matrix, okay? So we can first re-derive the formulas for 2 by 2 and 3 by 3, but even more importantly that we know how to compute determinant of an arbitrary and large matrix, okay? Even if I gave you the formula for the big formula for the determinant, which I will, if you had a matrix already 100 by 100, you would never want to use it, right? Because imagine what is 100 factorial. You would never be able to compute anything like this. 100 factorial terms. Forget about that. So there is a better way to compute determinant, and that's what we are going to work towards now. Okay. So the key trick again is our good old friend Gaussian elimination. Here it's sort of nice because here all the matrices are square, which makes our life a little bit easier. Remember how we were struggling with the 4 fundamental subspaces and so on? That was to deal with the case when the matrices were non-square. So here it's relatively easy. Here we are dealing just with square matrices. So if we apply Gaussian elimination to a square matrix, it involves, well, even for non-square matrix, it involves the 3 elementary operations, right? Flipping 2 rows, multiplying a row by a scalar. That's in particular if we need to bring it to the reduced row echelon form, which I think now you are experts on after the midterm. And adding a multiple of one row to another. So those are the basic operations of Gaussian elimination. And you can see that they nicely map to the defining properties or to the properties of the determinant, maybe some of the properties we just proven, right? So let's see how these elementary transformations change the determinant. Okay. So let's say that E is a matrix corresponding to one of these elementary operations. So then we know that these elementary operations can be written as matrix multiplication, right? And you hopefully remember how the E matrix looks like from the previous part. And let's take a look at how the elementary operations change the determinant, okay? So the type 1 operation means interchanging two rows of the matrix. Well, that's already by definition, right? I said by definition, the determinant, if you flip the rows, then you flip the sign, okay? So if my matrix B is matrix A after a type 1 elementary operation, then the sign of the determinant flips. Type 2 operation, that means multiplying row by a scalar. Well, that's also easy to figure out what does it do to the determinant, right? Because we have the linearity of the determinant, right? So multiplying row by a scalar by the linearity property, like property number 3. Here. This one. That means that we multiply the determinant by alpha, okay? And the third operation, adding a multiple of one row to another. Well, we have just shown, that's what I have shown here, that doesn't really change the determinant, okay? So if B is a matrix which I get from A by adding a multiple of one row to another, I get the same determinant as I started with, okay? So that's nice, right? So what we need to do now is to compute determinants of the elementary matrices. So let's take a look at them. And we'll take a look at them in the case of 4x4, but it's just for illustration, for just to make it a little more readable. For n by n matrices will work exactly the same way. Okay, so type 1 elementary transformation, that means interchanging two rows of a matrix. So the corresponding elementary transformation matrix looks like this. This would be like switching the first and second row, right? So the determinant of this, that's easy to figure out, right? What's the determinant of this? That's basically just flipping two rows of an identity matrix, right? We know that identity matrix, that's the first defining property of the determinant, has determinant 1. Well, if I flip its rows, I have to multiply by -1, so the determinant of this matrix must be -1. Easy, right? Now the second elementary transformation matrix looks like this. So in this case, it would be multiplying the second row by alpha. So how do I compute this determinant? Well, very easy, right? Again, directly by the linearity property. So this is just identity with one of the rows multiplied by alpha. By linearity, that means that's alpha times the determinant of identity. The determinant of identity is 1, so this is alpha. Simple, right? And finally, the third one, that's also simple. So that's the matrix that takes a multiple of one row and adds it to another. So in this case, it would be taking the first, scaling the first row by alpha and adding it to row number 3. So what's the determinant of this matrix? Well, again, that's what we have just said before. This is just the same matrix applied to identity, right? Again, you know that the determinant of identity is 1. And we know that adding a multiple of one row to another does not change the determinant. So this must be the same as the determinant of identity, which is 1. Okay. So the determinant of this elementary transformation matrix is 1. So the determinants of the elementary transformation matrices are simple. And that's the key idea. That's how we can get a determinant of arbitrary matrix if we use Gaussian elimination. So let's see. So from the rules we discussed before, we can summarize it like this. So if E is one of the three elementary matrices, we can say it has this effect on the determinant, right? That's what we have just discussed. So I guess we can, I don't know, we need to go through that basically again. So let's see. So if it's type 1, well, okay, maybe I can do it like this. So let's go through the three types. Okay, if E1 is a row swap, so that means it's a permutation matrix. Okay, so the determinant of E1A. So we know by the definition of the determinant, if we swap the rows, it's minus determinant of A. Okay. And on the previous slide, I argued that the determinant of E1 is minus 1. Okay. So I can write this minus 1 as determinant of E1, and therefore I have this formula. Okay, determinant E1 times A equals determinant E1 times determinant of A. Okay. It turns out that for the other elementary matrices, it works basically the same way. So E2 is the matrix which multiplies one of the rows of A by alpha. So it changes the determinant by alpha, that A. But we know that the determinant, that's what we did here, right? Luckily, the determinant of E2 is also alpha. So I can just write it like this, like determinant of E2, determinant A, okay? And for the third type, that's the matrix, the E3 is the elementary matrix which takes a multiple of one row and adds it to another row. So we know that does not change the determinant of A. And as I have shown you here, the determinant of E3 is also 1. So I can indeed put there E3 determinant A. Okay, so this is indeed true for all the three types of elementary matrices. So that's nice because now we don't have to remember which was which, because this is true for all of them. So that's neat. And now you can realize that for if we take any invertible matrix, then we can get it to reduced row echelon form. And the reduced row echelon form would be the identity, because we are talking just about square matrices. Okay. So if this is my sequence of elementary row transformation matrices which bring A to reduced row echelon form, which in the case of a square invertible matrix is just identity, right? We have been through this many times in the previous, I guess in the first part of the course. And we know that all of these matrices are invertible, right? That's how LU decomposition worked. So we can now take the determinant of both sides of this equation and apply what we learned there, right? So if these are if these two are identical matrices, then the determinant, of course, also has to be identical, right? We know the determinant of identity is 1, and we know that the determinant of this product of matrices, we can apply this rule to it, right? So that, I guess, if I was gonna do it one by one, then I would say that the determinant of this whole sequence of matrix products would be the determinant of E1 times the determinant of the rest, EKA, right? Then I would apply the same thing to E2 and so on until I would get that I can just split it into the individual determinants. Okay? Just applying this rule one matrix at a time. Okay? And because all these matrices are invertible, that means, oh, no. That's because, right, so we know what the determinants of the elementary matrices are, right? So the determinants of the elementary matrices are either -1, alpha, or 1, right? We would never want to be multiplying by with alpha equals 0. That would not be a good idea. And therefore we can take, invert this number, okay? So don't get confused. This is just an inversion of a scalar. That's not an inversion of a matrix, okay? So from this we can compute what exactly is the determinant of A, right? We just need to divide by all these determinants which we know are non-zero. So this basically tells us how we can compute the determinant of an invertible matrix. Okay? And importantly, what is the computational complexity of this compared to the n factorial formula? So using this, you could already like go ahead and write an algorithm to compute the determinant of a matrix if it's invertible, right? How fast it would be. What you would do, you would first run a Gaussian elimination that would produce a sequence of the elementary transformation matrices, right? Then we already know what the determinants of these elementary transformation matrices are. Well, we can certainly take 1 over that and multiply it together, and we get the result, okay? So what would be the time complexity of that? Hmm?
Is it just the complexity of Gaussian elimination?
Yes, exactly. The bottleneck there is the Gaussian elimination, right? Because once you have run the Gaussian elimination, it's sort of trivial to figure out the determinants of these things. I mean, it's just this, right? Once you know what type of elementary matrix operations they are, you know the determinant. You don't have to do any compute. So just multiplying them together, that's a negligible time. So indeed, the bottleneck there is computing the Gaussian elimination. And what is the complexity of Gaussian elimination if I have an n by n matrix? As n cubed, exactly. So if you were to compute determinant this way, you would get an O n cubed algorithm. That's a huge, huge improvement compared to n factorial, right? This is infinitely faster than n factorial. Like for n equal 100, this is something you can do no problem in MATLAB. Try doing 100 factorial. Good luck. Okay, so this is for invertible matrices. Determinant is incredibly useful also for singular matrices, and that's what I would like to explain next. So we want to basically connect invertibility and the concept of determinant, okay? So the first very simple fact we can realize is what is a determinant of a diagonal matrix. Well, I guess I could probably not show you this. I hope you haven't seen it. And ask you what is a determinant of a diagonal matrix. Well, I guess that's silly because you've probably seen it. So the determinant of a diagonal matrix is very simple because all we need to do is apply the linearity property. Careful about the linearity. You know that I mean linearity with respect to every row, right? With respect to every row, it tells me that I can pull the coefficient outside and replace it with 1, right? And ultimately, I will get that's a product of all the numbers on the diagonal times the determinant of the identity matrix, which is 1, right? So the determinant of a diagonal matrix is really simple. It's just the product of all the numbers on the diagonal, okay? And that's for arbitrary dimension matrix. So for a diagonal matrix, dimension 1 million, you can compute it in linear time. You just like multiply all the numbers together. Okay, so what if the matrix is not diagonal? Let's take a look at this, product of the pivots. So here I would like to show you that the absolute value of the determinant of the matrix is equal to the absolute value of the product of the pivot elements. So we will consider 2 cases. The first case is when the matrix A is invertible, okay? In that case, after we do the Gaussian elimination, then all the pivot elements will be non-zero. I guess I had a bug in the slide before, it means non-zero. And we only need the type 1 and type 3 operations because I don't need a reduced row echelon form, I just need the row echelon form. I don't need the ones on the pivots. I'm fine with any non-zero numbers as pivots, okay? So type 1 and type 3, they have an interesting property, because remember, the determinants of the type 1 and type 3 matrices, they were only -1 and 1. Okay. So that's the interesting thing is that here, when I apply all these elementary transformations of type 1 or type 2, they don't really change the value of the determinant, only it's a sign. Okay. This whole thing can only have determinant plus or -1. Okay. So here it's written down. So basically, after I take absolute value, then this becomes completely irrelevant. That's what's written here. Okay. So the determinant of this from the rule before, it splits. So this E is the product of all the elementary transformation matrices. We know that the determinant of E is only plus or -1, because all of these determinants are just 1 or -1. So after I take absolute value, this plus -1 doesn't play any role at all. And it's just the determinant of A. And that is of course equal to the determinant of the diagonal matrix, which, as we had just said, it's just the product of all the pivots, okay, in the absolute value. I take the absolute value to make the sign being irrelevant, okay? And now let's contrast it to, let's take a look at the case when the matrix is not invertible. So what happens if my matrix is not invertible? Well, what happens, I can do the same thing, okay? But what happens is that one of the pivots is going to be 0, okay, somewhere in there. The rest is the same. I can use just type 1 and 3 elementary operations. But everything else still holds, okay? The determinants of these are still going to be just plus or -1. So after I take the absolute value, I just get the absolute value of the product of the pivot elements. But here, the product of the pivot elements must be 0, right? Because I have 1 0 there, which turns everything 0. Okay? Which means that the absolute value of the determinant is 0, which means that the determinant is 0, because absolute value is only 0 for 0. And from this we can conclude an important thing, that determinant essentially tells us if the matrix is invertible or not, which is quite cool. Because if the matrix is invertible, just as I argued, I guess 2 slides before, then we get the non-zero determinant. And if the matrix is singular, then we get a 0 determinant. I could also write it like this, that A is singular if and only if, that's what this if means, if and only if the determinant of A equals 0. Okay? So that tells you the determinant is quite a useful thing. If somebody tells you the determinant, you immediately know if the matrix is singular or not. Even better, if you are doing like numerical computations and you have the determinant for 2x2 or 3x3 matrices, no problem to compute a determinant, right? Then if the determinant is close to 0, then you can sort of argue that the matrix is close to singular. Maybe not like perfectly mathematically singular, but numerically close to singular. Okay, so now I would like to generalize this product rule. So we have this product rule for elementary matrices. So before we have shown that if I have any elementary matrix and multiply with A, then I have this property, that it doesn't matter if I do the matrix multiplication first and then take the determinant, or if I first take the determinants and then multiply them, the result, the scalars. It turns out this is true for arbitrary 2 matrices, not just for the elementary transformation matrices, which is quite nice. Is it? So how can we prove this? Let's try to prove this. Let's try to prove that determinant of A times B is equal to determinant of A times determinant of B. And again, keep in mind this AB, this invisible operation here, this is matrix multiplication, and this is just a scalar multiplication, okay? So we will consider two cases. This is case number 1, this is case number 2. So in the first case, that either one of them is singular, okay? Either A or B is singular. From this it follows that the product is also singular. And this basically then says that 0 is 0, okay? Because if AB is singular, we just said the determinant of singular matrix is 0. And here I have either determinant of A is 0 or either determinant of B is 0. So that's either way it's 0, because 0 times anything is 0. So then this just reduces to 0 equals 0. As simple as that. By the way, can you give me a quick argument why if A or B is singular, then the product is also singular? Let's make it more specific. Let's assume that B is singular. If B is singular, why is the product A and B also a singular matrix? Without using this formula, because that's what we are trying to prove. Yep?
So if B is singular, then one of its rows is all zeros. Or you can reduce it to a form of all zeros.
You can do what?
You can reduce one of its rows to having only zeros since it's missing.
You can reduce, yeah, that's correct.
So then the product of A and B will have a row of all zeros.
Correct.
Therefore, it's singular.
Nice, yeah. That's a good argument using Gaussian elimination. Yes, you can spin the argument in many different ways. You can like look at the column space of B, for example, and then say that by applying A, or row space of B, and by applying A, the row space doesn't change. So if the row space was deficient, it wasn't full rank. Then certainly by multiplying of A, it cannot grow. So it will still be singular. Yeah. You had the right idea. Okay, so one of them is singular. We are done. And what if that's not true? What if both are invertible? Well, if both are invertible, then I can convert A to a product of elementary matrices, right? So A will be just a product of elementary matrices. In this case, I need the type 2 matrix 2. So I get there some actual numbers. So then we already know that for elementary matrices, we can split the determinant into the individual pieces, right? That the determinant of A, of course, these are the same matrices, so the determinant must be the same. And we know for the elementary matrices that it doesn't matter if I do the matrix multiplication first and the determinant, if I first take the determinant and then multiply the determinants together. So that's true for A. And if I put there the B, then I can still take out the individual elementary transformations, okay? That's the same as before, right? I first apply it to E1. That's why I get E1 out of it. Then I would take E2, applying iteratively the same rule, and I get this. Are you following me? I hope. And then you can notice that this product of D, that's what I have here. So that's nothing but determinant of A. So that's what I have here. So indeed, the determinant of A times B is the same as determinant of A times the determinant of B. And I needed the fact that A is invertible, but if it was not, then the first one applies, so it's all cool. Okay. Yeah?
It shouldn't be inverse, like determinant of A equals the determinant of E1, E2 to EK inverse.
Why would there be an inverse?
Isn't that how we
Oh, well, no, that was before it was something else. Here I see what you were saying.
it can still be rewritten.
I mean, it doesn't really matter, because if you invert it, you still get elementary transformations, right? Yeah, I could write it with the inverses, right? I could just write inverse everywhere here. The argument won't work exactly the same way, but I guess it's easier not to write the inverses because we don't have to. 'Cause inverse of an elementary transformation matrix is an elementary transformation matrix, period, right? Okay. Speaking of, so remember this product rule. That's a very important thing. If you need to compute determinants, that's super useful. here is how it's useful. Here, as you were talking about inverse, here we can easily show what's the determinant of an inverse matrix, which is sort of cool. So let's take a look at this. So the first bullet point. From the fact that we just derived that the determinant of the product is the product of the determinants, we can show what is the determinant of A inverse. So let's take a look at it. So if I take determinant of A inverse, well, on one hand, this needs to be equal to determinant of identity, right? Because A inverse times A is identity, and the determinant of identity is 1, right? It's the first defining property. On the other hand, we have this product rule, right? So this needs to also be equal to determinant of A times determinant of A inverse, okay? Well, from this, I have to conclude that determinant of A times determinant of A inverse equals 1, of course. And that's why the determinant of A inverse is just 1 over the determinant of A. Okay, that's what I have here. And here you can also nicely see why I need to assume that the matrix is not singular. Because what would happen if the matrix A was singular? Would not be good, right? But the inverse would be undefined, and here I would be dividing 1 by 0, which is also not good. So it sort of makes sense, right? And the other thing that sort of clears the confusion, that the second bullet point here, oh, is that clear, the first one? The determinant of an inverse matrix. Remember this. So here you can sort of start seeing how the determinant really characterizes the matrix, right? That it sort of relates to all the operations we had before. It relates to matrix multiplication. It sort of converts matrix multiplication to scalar multiplication, and sort of converts inverse to just inverting a scalar number. So you can see the determinant really tells you a lot about the matrix. And the second bullet point here that sort of clears the confusion which I had there before about the rows or columns, because it says that the determinant of A transpose is equal to determinant of A, which means that because we are talking about square matrices, and A transpose essentially says take rows and make them columns, okay? So from this implies the corollary of this. It's a mouthful. The corollary of this property is that whatever we showed for rows applies equally for columns, because we can apply this property which turns rows into columns, and the determinant doesn't change. So let's take a look. How do we prove this? Let's see. How do we prove this? Well, I guess we can again consider two cases, right? So if A is singular, then of course also A transpose is singular, right? I guess your argument would still apply, right? So of course, in this case, we again have 0 equals 0, so nothing particularly deep. So that's true. Let's check. The second case is that A is invertible, non-singular. Well, in that case, I can write A as a product of elementary row transformations, right? And what I would like to do would be to look at what is AT. What is AT, by the way? Oh, sorry, it was supposed to be some K or something. A product of a bunch of elementary row transformations. So if I want to do AT, I have to apply the product rule to transpose. I hope you remember that. So tell me, what is AT in terms of the elementary transformations E? Well, there's going to be E something. Well, yeah, but what's going to be here? No. Yeah, I called it K here, so let's give it a K. That's the only trick there, right? That the transposition, that's this rule. That's the AB transpose equals B transpose A transpose. Just apply to a bunch of terms, one by one, just like I was saying a million times before. Okay, so all we need to figure out is what the determinants of the transposed elementary row operations will be. Okay, well, let's take a look at them. So the first type was a permutation matrix, right? So the E1 type, sorry, now this is a confusing notation. Okay, let me call this E perm or something. So this was a matrix in general that this is index I, and this would be index J here. So the matrix looks like identity except for these four guys, which perform the swap of row I with row J. Okay. I guess I only had it before in the 4x4 case. That's what I had here. This one. So this is for like a swapping journal of row I and J. Well, in either, and here would be just once, right? Everywhere else. So what you can see immediately about this matrix, it's symmetric. Okay, like it's obvious here. This matrix clearly is symmetric, right? If I take the rows, make them columns, I don't really change anything. It's a symmetric matrix. Symmetric matrix means that AT equals A. I will take it away because I don't want to assume that this was symmetric. Well, that means that doing the transposition doesn't change anything because it's symmetric, so it certainly doesn't change the determinant. So the determinant is going to be the same thing. So what was the determinant of this matrix? So, okay, let me ask you this way. What is going to be the determinant of E perm, the permutation, arbitrary, not permutation, maybe I could call it switch, right? This is the point of the lecture when I'm getting tired and making mistakes. So watch me. So this is switching rows I and J. What is the determinant of this matrix? -1, right? I guess the point is that the matrix to swap two columns would be exactly the same. Or the matrix is symmetric, so it's transpose. Okay, I will write it. So the determinant of E switch transpose equals the determinant of E switch, which equals -1. So the determinant hasn't changed. So that's good. What about the scaling one? So the E scale. Well, that was just a matrix, which is again just an identity almost everywhere except at one row number I stick in alpha. Okay. So again, the same story. It's also symmetric, right? So the determinant is alpha, exactly. So it hasn't really changed, okay, by transposing it. I could write the same thing for the scale. Determinant of transpose E scale is the determinant of the non-transpose one. It's also alpha. Okay. So far it's promising. So how about the last one? So that's I guess the elimination operation. So if I transpose that one, so that was this, right? So here it was the elimination on rows. Okay. What happens if I'm doing an elimination on columns? This means that then I have to transpose it. So the alpha goes here. So in general, the transpose elimination matrix looks like this. What does it look like? So I have identity here. I have all ones, and one of the, I guess I could say columns has alpha here. Okay. So what is the determinant of this matrix? I mean, the only difference is that before the alpha was here, right? Before the transposition. So what is the determinant of this matrix? Can you? Yes. No, it's still, well, let's take a look at it. Let me do this a little bit properly. It's easy to get it wrong. Oh, let me write it, and now this notation is actually gonna be handy. So if I have ones everywhere, here I have some alpha here. So I can split the determinant into like big identity, right? plus what I'm going to have here. So I have 1, 1, and here where the alpha was, then I'll have 0, and alpha is still there, and I have 1s going on here. Okay. So what I did, I split it. I took this row and applied the linearity with respect to this row, right? So here I got just identity, just all 1s and 0s everywhere else. And here I took the 1 out and just got alpha, okay? Well, the determinant of identity, that's 1, right? And this is just a matrix. I can just eliminate this alpha by taking alpha times this row, and I'll get a matrix which is diagonal and one of the pivots is 0, okay? So the determinant of this is 0. Okay. So I guess this was a long way of saying that the determinant of the transposed elimination matrix is also alpha. Okay. And from this, we are almost done, because then all I need to do. So we are proving the determinant of A transpose is equal to determinant of A. So the determinant of A transpose is the determinant of EK transpose times E1 transpose, right? We know that for all matrices this is true, right? EK transpose to E1 transpose. And what we have just discussed at length is that this is actually equal to determinants of the non-transpose matrices, okay? I discussed all the 3 cases. In all 3 cases, if I transpose the elementary matrix, I ended up with the same determinant it had before transposing it, okay? So what that means that I can just bring it back, right? I can just do determinant. I can certainly, here I can actually arbitrarily swap the order, because those are just scalar numbers and they commute, right? In matrices I couldn't do that, but in determinants I can do that. So I guess let me do that slowly, baby steps. Now I can again use the product rule of determinants, so I can bring it together. But this is what I began with. This was my A, right? So indeed, the determinant of a matrix does not change by transposing it. So that you could say that the determinant is invariant to transposition, I guess. All right. And the last thing I would like to show you is the big formula. Because I sort of started with telling you what the determinant is for 2x2 matrices, so I should still be able to derive it from our new definition, right? To sort of close the loop, if you will. So let's derive using our rules now. What is the determinant of A, B, C, D? Okay. The idea is quite simple. I take this first row, A, B, and I rewrite it as a sum of 2 row vectors, A0 plus 0B, and I apply linearity. Okay. So what do I get if I do this? Well, I get A0 CD plus 0B CD. Okay. And now, well, it worked so well for the first row, why don't I use it for the second row as well, right? So CD certainly can be decomposed in exactly the same way. So what do I get is A0, C0, so that's decomposing the first term. A0, 0, D plus, and same thing on the second term, so 0B, and here I will have C0 plus 0B, 0D. Okay, got it? I just applied the linearity of the determinants, one of the defining properties, twice. Well, then you can see that here is a column of zeros, right? So the determinant of this is 0. Same thing here. So these guys are out of it. And the determinant of this matrix, well, what is it going to be? Again, I can apply the linearity, right? So that means if I take A and D out of it, it's going to be AD times the determinant of this matrix. Does this matrix look familiar? And here's going to be CB times this matrix, 0, 1, 1, 0. Okay. What's the determinant of this matrix? Hope to 1. What's the determinant of this matrix? You have two choices, two up to possibly. -1, right? And indeed, what I recovered is the formula I started with, or CB doesn't matter, right? These commutatives are just scalars. So indeed, the formula for 2 by 2 can be really derived from these properties, so that's good. How it would look like for 3 by 3? For 3 by 3, that's this. I guess here I can tell you how it was derived in the first place, or it can be derived in the first place. So I could basically be doing exactly the same exercise. I can say that this is A00 plus 0B0 plus 00C, right? And I get an expression here which would have how many terms? 27 terms, right? Here I had, yeah, 2 times 2, that was 4 terms. Here I had 3 times 3 times 3, which is 27. But okay, let me write just the non-trivial ones there. Okay, just the ones. Okay, let me write down just the ones that don't have a full column or row of zeros. Okay, because I know these are immediately all zeros. Okay, so the non-trivial ones, there is this A, E, I. It's my favorite. And here is the B. Oh, sorry. Here's 0, B, F, G. Maybe I could just put the zeros there, right? To make it a little neater. Plus 0, 0, C, D, 0, 0, 0, H, 0. That's the first bunch. You know what? I'll write it here. No, I'll write it here. The second bunch is 0, 0, C, 0, E, 0, G, 0, 0, plus, let's get this right, so this is 0, B, 0, D, 0, 0, 0, 0, I, and the last one is A, 0, 0, 0, 0, F, 0, H, 0. Okay? If you want to do this for a homework to really write it like this, you can, and then discard the ones that have all whole columns or rows of zeros. But then the next step is the same. So here I just factor all them out, and I will get here these matrices. Let me skip the zeros in the interest of time. So this would be 1, 1, 1 here. This would be, oops, too fast, CDH, 1, 1, 1, GEC, 1, 1, 1, 1, 1, 1, oh, DBI. Okay, it's getting really late. Maybe we should finish this on Wednesday. HHF, 1, 1, 1. Okay. Now we need to compute the determinants of these elementary matrices. But the cool thing is that this is of course 1, right? What is the determinant of this matrix? Let me put the zeros there to make it easier. Again, you have 2 possibilities. It's actually not, because here I can actually get it to identity by 2 row swaps, right? If I do 2 flips, then the -1s cancel. So this, the determinant of this actually is 1. Okay, you see that? I do 1 row swap to get the 1. So okay, let me do this really slow, and then I will, I guess, finish it on Wednesday. So this is equal minus this, and this is equal minus minus. So I guess -1 times -1 to make it really obvious. 0, 1, 0, and that's flipping the second and third. This, right? This is 1. This is 1. Everything is 1. Same way you could see that this one is also 1. And these you can get to identity by just one row flipped. So these are all determinants minus 1. Okay? This is how do I get the determinant formula for a 3 by 3. And I'll show you the big formula next time because it's already time and the big formula is big. So I'll show that to you on Wednesday. Okay? Any questions? Okay. Thank you very much.